Just now we defined that IC 1 minus alpha, alpha IB plus IC naught. So once again I am trying to convey that IC of 1 minus alpha plus alpha IB plus IC B naught. So IC is equal to alpha by 1 minus alpha IB plus 1 by 1 minus alpha IC B naught. That there will be having a relation between common base and common emitter as well as common collector configuration, where alpha defines the amplification factor of common base configuration, where the output current by input current. In common base configuration, according to alpha, the output current is IC and the input current is IE, so that from the common emitter configuration, the amplification factor, from the common emitter configuration, the amplification factor is beta. In common emitter configuration, the output current is IC and the input current is IB. So that I am defining that beta is equal to IC by, from the transistor definition, we know that IE is equal to IB plus IC and IB is equal to IE minus IC. This already we know that from the basic working of a transistor. So that in the place of IB, I can consider it as IE minus IC. This is equation 1. Dividing numerator and denominator by IE. If I am dividing numerator and denominator by IE, then beta is equal to IC by IE by IE by IE minus IC by IE. So once again I am trying to highlight the importance of this. By dividing numerator and denominator, of course, beta is equal to IC by IE by IE by IE minus IC by IE. From the common base configuration, we know that alpha by 1 minus alpha. That is a relation between the amplification factor of common base configuration as well as common emitter configuration. From this basic relation, I am concluding the equation of a transistor which is using in common emitter configuration. IC is equal to beta into IB plus, as we know that 1 plus beta is 1 plus alpha by 1 minus alpha. This I can conclude that 1 by 1 minus alpha, so that 1 plus beta of IC B naught. So IC is equal to beta IB 1 by, of course, plus 1 minus alpha, even we can consider it as 1 minus alpha also, IC B naught. So that is a current equation for common emitter configuration. Of course, now I am trying to differentiate this current equation with respect to the IC naught, so that I can find out the stabilization factor. So 1 plus beta is concluded as 1 by 1 minus alpha. This can be concluded as 1 minus alpha plus alpha by 1 minus alpha, so that I can equate as 1 by 1 minus alpha. So in this place, 1 plus beta will be concluded. Anyway, now I am trying to frame that equation. IC is equal to beta into IB plus 1 plus beta of IC B naught. In some textbooks, they are considering as beta into IB as 1 CE naught, where CB naught is common base with input is open, where CE naught is common emitter with input is open. Almost all will give the same value only. This is the final equation what I am considering. Now I have to differentiate with respect to stability factor with respect to reverse saturation current to find out the stability factor, that we know the basic definition as change of collector current with respect to change of reverse saturation current. Applying this condition, you consider this is equation 2, differentiating with respect to IC naught on LHS and as well as RHS quantity of equation 2. So by differentiating equation 2 with respect to IC naught, then the above equation will become as change of collector current with respect to change of reverse saturation current beta into change of IB with respect to change of IB naught plus, of course, 1 plus beta into change of IC naught into change of IC naught. These two almost are equal. IC B naught is equal to IC naught. So that according to this definition, this quantity is becoming as unity, and IB is input current is depending upon almost all. Here in this case we are considering input current is always constant. From the input current only output will be affecting, so that I can consider this value is equal to 0. Then the stability factor for common emitter configuration is change of IC naught with respect to change of IC is equal to 0 plus 1 plus beta. According to the basic operation of a common emitter configuration, as we know that beta is change of collector current with respect to change of base current. If you carefully observe this, IC is equal to beta into IB. From the operation of a transistor, among three currents, IE is equal to IB plus IC, always IB current is minimum. So from this definition, IC is equal to beta into IB, always beta is minimum. But the collector current is maximum. In order to achieve maximum collector current, we can't increase the IB. IB is always minimum. So obviously the another term which is high, beta is very high value. Beta is very high, so that multiplying a high value with low value, overall value is also high. That's why the collector current is high. If you carefully observe that the RHS quantity consisting of two terms, one is beta as well as IB. In this product, IB is always minimum. The other value which is high value is beta only. So always we are considering is beta is very high. From the definition of stability factor of common emitter configuration, just now we derived that in the previous slide that S is equal to 1 plus beta. S is stability factor for common emitter configuration. In this case, beta value is very high, so that the stability factor is 1 plus beta. So 1 plus beta is a very high value. That's why the stability factor overall value is very high. If the stability factor is high, then the circuit is less stable. So what do you understand from this? If the stability factor is very high means what? That is indirectly it is a change of collector current with respect to change of reverse saturation current. When the numerator value increases means what? It is highly depending upon the change of collector current. Of course, because of the reverse saturation current. As reverse saturation current is increasing, obviously the numerator value is also increases. Then it is not good for the circuit. Indirectly the circuit is less stable. Why? Because the collector current the collector current must be depending upon the input current only, but the collector current is depending upon the reverse saturation current. That's why the circuit is less stable. So to maintain this stability or to increase the stability of the circuit, we have to see that always the operating point at the center of the DC load. If that particular circuit is less stable means obviously the operating point is trying to shift its position from active region to saturation region or from saturation region to cutoff region. So being an electronics engineer, if you are concentrating designing the stabilization circuit, always we have to see that the stability factor must be minimum. This is a basic concept what I want to concentrate about the stability factor. Now we will try to find out the stability factor of the each circuit. This is a basic definition of a stability factor, but according to the definition of common emitter configuration, what actually the stability factor will defines, that we will try to find out once again. So as we know that the collector current IC is equal to beta into IB plus 1 plus beta into IC B naught. Now once again I am trying to differentiate with respect to IC naught, differentiating both sides with respect to IC naught, beta into change of base current with respect to IC naught plus 1 plus beta into change of IC B naught with respect to IC naught. Now I am trying to concentrate this. So the stability factor is defined as DIC by DIC naught. This is the stability factor. Now IB I am considering as constant, beta into 0 plus 1 plus beta into this quantity is equal to unity, then stability is equal to change of collector current with respect to change of IC naught is equal to 1 plus beta. This is very high value. The next, we'll find the stability factor. IC is equal to beta into IB plus 1 plus beta into IC B naught. Now actual meaning of stability with respect to common emitter configuration. Stability factor with respect to common emitter configuration. Previously we concentrate the basic definition of stability factor which is applicable for common base, common emitter or common collector or any configuration we have to consider. That is the basic definition. But according to the common emitter configuration, the stability factor will differentiate according to the type of circuit what we are using. Now you consider this is equation 2. Differentiating equation 2 with respect to IC. Differentiating equation 2 on both sides with respect to IC. So differentiating DIC by DIC. For time being, the partial differentiation I am considering as dou IC. All will give the same meaning only. In this case, what I am considering, dou IC by dou IC is equal to beta differentiating with respect to IC plus 1 plus beta differentiating IC B naught is equal to IC. In the previous session, in the previous discussion also I am coming across that IC B naught is equal to IC naught. So that this value is equal to 1 beta into change of base current with respect to change of collector current plus 1 plus beta. This I am considering as IC naught by dou IC. So once again I am trying to highlight that equation. 1 is equal to beta into change of IB by change of IC plus 1 plus beta into change of IC naught by change of IC. So that this stability from the basic definition, change of IC by IC naught. So this already we know that I am considering in the above equation, beta into change of IB by change of IC plus 1 plus beta by 1 by S. So that I have to find out the stability factor. So S is equal to 1 minus, of course, from the definition. So I can consider that, once again, one plus beta into 1 by S is equal to 1 minus beta into change of IB by change of IC. So that S is equal to 1 plus beta by 1 minus beta change of IB by change of IC. This is a final stability factor for CE configuration exclusively. So just now I defined the 4 important circuits what we are using for transistor biasing stabilization purpose. One is a fixed bias circuit, another one is emitter to base bias circuit, collector to base bias circuit, and self bias or voltage divider biasing circuit. Among these 4 biasing circuit, how can we choose that which one is the best circuit? Based upon this particular stability factor only. That's why I'm spending more time on defining this stability factor. By using this stability factor only, we are concluding that which circuit is the best circuit. In that process, the first one is fixed bias circuit. Fixed bias circuit. So I am trying to define the diagram of the fixed bias circuit. This is the transistor. From this definition, I am concluding the resistor and the fixed biasing. This is the RB and this is RC and this is VC. Of course, I am using common emitter configuration. Why? Because in common emitter configuration only the stability is minimum. We are getting less stabilization circuits. So to increase the stability only, we require the stabilization techniques. That is the reason. And this is VBE. Of course, this is IC and this is IB. How can we define that this circuit is best or that circuit is best? Because depending upon the stability factor. And that stability factor, before finding that stability factor, first we have to locate that at which point the DC load line and the operating point is existing for this circuit. In order to locate this operating point as well as DC load line, we require the basic considerations or by applying the KVLs on the above circuit. So I am considering the 2 paths. This is path 1. And this is path 2. So one thing what we have to consider, and the output is taken across here, this is VCE. So I am considering 2 paths. One is path 1 and the other one is path 2. Applying KVLs on path 1 as well as path 2. First initially I want to locate the DC load line and after that I want to locate the operating point. For locating the DC load line, first initially we have to locate the DC load line and after that we have to locate the operating point. After finding these two only, we can say that whether the transistor is continuously operating in active region or not. So in order to locate the first initially the DC load line, we require the 2 conditions. One is VCE maximum when IC is equal to 0. The next one is IC maximum when VCE is equal to 0. So from this definition, first I want to concentrate the DC load line of a fixed bias circuit. Why it is called the fixed bias? I am using the fixed connection across the base terminal. This is emitter, base and collector. I am using a fixed bias through RB resistance to the input of this transistor. That's why it is called the fixed bias circuit. Anyway, first I want to locate the DC load line. So for that purpose, applying the KVL to path 2. Apply KVL to path 2. So if you carefully observe the previous circuit, if you apply the KVL to path 2, the total voltage VCC is equal to ICRC plus VC. This is a final equation of path 2 by applying the KVL. I am using the same equation. So VCC is equal to ICRC plus VCE. So first I want to locate the DC load line. For that purpose I am taking the condition VC is equal to 0, in which IC is equal to IC maximum. This is the first condition. So you consider this is equation 1 and this is equation 2. Similarly, IC is equal to 0, where VCE is equal to VCE maximum, that value is equal to VCC. So this is equation. Apply 2 and 3 in above equation. In equation 1, so that I am getting as VCE maximum is equal to VCC, IC maximum is equal to VCC by RC. So these are the 2 points what I am locating initially for DC load line, and after that I am concentrating the operating point. So I located DC load line here. Once if you come across any numericals, then you will try to understand. Later I will try to go for the numericals. First I am concentrating on theoretically how we are concentrating DC load line as well as operating point. These 2 points are required to locate DC load line. Similarly, I want to locate the operating point. So operating point is nothing but Q point. I want to locate IC, VCE. For that purpose, I am going the previous circuit as applying KVL to path 1. So by applying KVL to path 1, so that I am getting as VCC is equal to IBRB plus VB. So this is, once again I am trying to frame the equation by applying the KVL to path 1. I am taking the help of the same equation in the locating the operating point also, so that I am writing the same thing, applying KVL to path 1, so that I am getting as VCC is equal to IBRB plus VB. So IBRB is equal to VCC minus VB. So IB is equal to VCC minus VBE by RB. This is the final input current what I am getting for common emitter configuration. Once you know IB, we can easily find out IC from the amplification factor beta. That already we know that. Beta is equal to IC by IB, so that IC is equal to beta into IB. So from this we can locate IC. This is the point what we are locating. From path 1 we are locating the IC value. Similarly, from path 2 of the above circuit, from path 2 we have to locate the another point of Q point. Q point IC is located. We have to locate VCE. IC is located from IB. Similarly, from VCE we have to locate by applying the KVL to path 2, so that we are getting VCC is equal to ICRC plus VCE. I want to find out the VCE. VCE is equal to VCC minus ICRC. So this is one more point what I located. So another point IC is located beta into IB. So these two are required to locate the operating point. So finally, I have located the DC load line as well as operating point for the fixed bias circuit. Now we have to find out the stability factor, whether this circuit is useful in a practical scenario or not. Already we know that from the basic definition of stability factor, S is equal to 1 plus beta by 1 minus beta into change of base current with respect to collector current. Here IB is fixed. IB is fixed. So that from the definition, IB is a constant value. So that change of constant or differentiating the constant with respect to IC, this value is becoming as 0. This value is becoming 0. Then the stability factor is 1 plus beta. It is a very high value. Very high value. So fixed bias circuit is not applicable as a stabilization circuit. Why? Because the stability factor is very high and the change of IB with respect to change of IC, almost all we are considering IB is constant. Differentiating any constant with respect to IC, then obviously it is not useful in a practical scenario. Why? Because this value is becoming 0 and finally the stability factor is 1 plus beta. From this we can easily conclude that fixed bias circuit is not applicable for stabilization of operating point or continuous working of a transistor to achieve the faithful amplification. In the next class we will try to conclude that why the fixed bias is not applicable for practical scenario by coming across one numericals. Thank you.